Hello everyone, welcome to the course on cryptography. So in today's session we'll discuss about Fermat's and Euler's theorems. The two theorems that play important roles in public key cryptography are Fermat's theorem and Euler's theorem. So first we'll discuss about this Fermat's theorem. This Fermat's theorem states the following: if P is prime and A is a positive integer which is not divisible by P, then A bar P minus 1 is congruent to 1 with mod P. So considering the set of positive integers that is less than p, that is 1, 2 till p minus 1, and multiply each element by a modulo p to get the set. This is equal to a mod p, 2a mod p till p minus 1 a mod p. So none of the elements of x is equal to 0 because p does not divide a. Further, no two of the integers in x are equal. To say this, assume that ja is equal to ka, where j lies between 1 and k. K is again less than or equal to p minus 1 because a is relatively prime to p. So we can eliminate a from both sides of the equation, resulting in j is congruent to k mod p. This last equality is impossible because j and k are both positive integers less than p. Therefore, we know that the p minus 1 elements of x are all positive integers with no two elements equal. We can conclude that the x consists of the set of integers that is from 1, 2 till p minus 1 is in some order. Multiplying the numbers in both sets p and x and taking the result mod p gives a into 2a into p minus 1 into a which is congruent to 1 into 2 into p minus 1 of mod p. So this leads to a bar p minus 1 into p minus 1 factorial congruent to p minus 1 factorial of mod p. So we can cancel this p minus 1 factorial term because it is relatively prime to p. So this leads to the equation as a power p is equal to a mod p. So an alternative form of this Fermat's theorem is also useful. If p is prime and a is positive integer, then a power p is congruent to a mod p. The first form of the theorem requires that a be relatively prime to p, but this form does not. So p is equal to 5 and a is equal to 3, then this can be written as a bar p is equal to 3 bar 5. That is equal to 2, 4, 3. So it is congruent to 3 of mod 5. Next is Euler's totient function. So this is related to Euler's theorem. So here we need to introduce an important quantity in number theory referred to as Euler's totient function. This function, written as pi of n, is defined as a number of positive integers less than n and relatively prime to n. So by convention, pi of n can be written as 1. So determining pi of 37 and pi of 35. Because 37 is prime, all of the positive integers from 1 through 36 are relatively prime to 37. Thus, pi of 37 can be written as 36. So to determine the pi of 35, we list all the positive integers less than 35 that are relatively prime to it. So 1, 2, 3 till 34. There are 24 numbers on the list. So pi of 35 is equal to 24. So and the list, the first 30 values of pi of n. The value of pi of n is without meaning, but it's defined to have the value 1. So it should be clear that pi of p is equal to p minus 1. So for a prime number p. Now suppose that we have two prime numbers p and q with p not equal to q, then we can show that for n is equal to pq. So this shows the sum of some values of Euler's quotient function of pi of n. So pi of n can be written as pi of pq, which is equal to pi of p into pi of q is equal to p minus 1 into q minus 1. To see that pi of n is equal to pi of p into pi of q, consider that the set of positive integers less than n is the set. So the integers in this set that are not relatively prime to n are the set, and the set q to q p minus 1 into q. Consider that any integer that divides n must divide either of the prime numbers p or q. Therefore, any integer that does not contain either p or q as a factor is relatively prime to n. Further, the two sets just listed are non-overlapping because p and q are prime. We can state that none of the integers in the first set can be written as a multiple of q, and none of the integers in the second set can be written as a multiple of p. Thus, the total number of unique integers in the two sets is q minus 1 plus p minus 1. So it can be written by the expression pi of p into pi of q. So next we'll see about Euler's theorem. Euler's theorem states that for every a and n that are relatively prime, a of pi of n is equal to 1 mod n. So this is true if n is prime, because in that case pi of n is equal to n minus 1, and Fermat's theorem holds. However, it also holds for any integer n. So pi of n is number of positive integers less than n that are relatively prime to n. Consider the set of such integers labeled as r is equal to x1, x2 till x pi of n. Each element xi of R is a unique positive integer less than n with GCD xi comma n is equal to 1. Now multiply each element by a modulo n. S is equal to ax1 mod n, ax2 mod n, ax pi of n mod n. The set S is a permutation of R by the following line of reasoning. Because a is relatively prime to n and xi is relatively prime to n, axi must also be relatively prime to n. Thus all the numbers of S are integers that are less than n and that are relatively prime to n. There are no duplicates in S. If ax mod n is equal to axj mod n, then xi is equal to xj. Therefore, it can be given by the equations as shown here. So as is the case for Fermat's theorem, an alternative form of the theorem is also useful. That is a bar pi of n plus 1 is congruent to a mod n. Again, similar to the case with Fermat's theorem, the first form of Euler's theorem requires that a be relatively prime to n, but this form does not. Thank you. Hello everyone. Welcome to the course on cryptography. In third module, now we are going to discuss about fields. A field F, sometimes denoted as F plus into, is a set of elements with two binary operations that is called as addition and multiplication, such that for all a, b, c in F, it following the axioms are obeyed. That is from A1 to M6. F is an integral domain, that is F satisfies the axioms from A1 through A5 and M1 through M6. The multiplicative inverse is for each A in F except 0, there is an element A inverse in F such that A into A inverse or A inverse into A gives 1. So a field is a set of elements in which we can do addition, subtraction, multiplication and division without leaving the set. Division is defined with the following rule, like A by B is equal to A into B inverse. So some of the examples of fields are the rational numbers, the real numbers and the complex numbers. So the set of all integers is not a field because not every element of the set has a multiplicative inverse. In fact, only the elements 1 and -1 have multiplicative inverse in the integers. In gaining insight into fields, the following alternate characterization may be useful. Like a field F is which is denoted by F plus is a set of elements with two binary operations called addition and multiplication, such that the following conditions hold. F forms an abelian group with respect to addition. The non-zero elements of F form an abelian group with respect to multiplication. Distributive law holds, that is for all A, B, C in F, so that A into B plus C can be written as AB plus AC. A plus B into C gives AC plus BC. So this figure actually summarizes the axioms that defines groups, rings and fields. Abelian group, the multiplicative, there is an element 1 in S such that we get, and similarly for additive. Thank you. Hello everyone, welcome to the course on cryptography. In today's session we'll discuss about finite fields of the form GF of P. In this section it is defined a field as a set that obeys all of the axioms as shown in this figure. It gives some examples of infinite fields. Infinite fields are not of particular interest in the context of cryptography. So in addition to infinite fields, there are two types of finite fields that can be seen in the figure. So when it comes to the types of finite fields play a crucial role in many cryptographic algorithms. When it comes to types of fields, fields with an infinite number of elements and finite fields, it is divided into two types. And this finite fields is divided into two groups. One is GF of P, that is finite fields with P elements. GF of P power n means finite fields with P power n elements. So the order of a finite field must be a power of a prime, that is P power n, where n is a positive integer. The finite field of order P power n is generally written as GF of P power n. Here GF stands for Galois field. This is in honor of the mathematician who first studied this finite fields. There are two special cases are of interest for our purposes. For n is equal to 1, we have the finite field GF of P, and this finite field has a different structure than that for finite fields with n greater than 1. So for finite fields of the form GF of P power n, GF of 2 power n fields are of particular cryptographic interest. And when it comes to finite fields of order P, for a given prime P, we can define the finite field of order P, that is GF of P, as the set ZP of integers, that is from 0, 1 to P minus 1, together with the arithmetic operations modulo P. Therefore, we are using ordinary modular arithmetic to define the operations over these fields. So, the set Zn of integers 0, 1 till n minus 1, together with the arithmetic operations modulo n, is a commutative ring. So we can observe that any integer in Zn has a multiplicative inverse if and only if that integer is relatively prime to n. If n is prime, then all of the non-zero integers in Zn are relatively prime to n. Therefore, these exist a multiplicative inverse for all of the non-zero integers in Zn. Thus, for Zp, we can add the following properties to those, that is multiplicative inverse. For each w belongs to Zp, and w is a non-zero element, there exists a z that belongs to Zp, such that w into z is congruent to 1 of mod p. Because w is relatively prime to p, if we multiply all the elements of Zp by w, the resulting residues are all of the elements of Zp permuted. Thus exactly one of the residues has the value 1. Therefore, there is some integer in Zp that when multiplied by w yields the residue 1. That integer is the multiplicative inverse of w, designated as w inverse. The Zp is in fact a finite field, and it is consistent with existence of a multiplicative inverse and can be rewritten without the condition. So if A into B is congruent to A into C of mod B, then we can say that B is congruent to C mod B. Multiplying both sides of equation by the multiplicative inverse of A, we have A inverse into A into B, A inverse into A into C. So this gives B is congruent to C mod B. The simplest finite field is its arithmetic GF of 2. Its arithmetic operation are easily summarized. Addition, multiplication and inverses we can see here. Addition is equivalent to the exclusive OR, that is XOR operation, and multiplication is equivalent to the logical AND operation. And finding the multiplicative inverse in GF of B. It is easy to find the multiplicative inverse of an element GF of B for small values of B, so that we can simply construct a multiplication table. And desired result can be read directly. So for large values of B, this approach is not practical. If A and B are relatively prime, then B has a multiplicative inverse modulo A. That is, if GCD of A comma B is equal to 1, then B has a multiplicative inverse modulo A. That is, for positive integer, B less than A. There exists a B inverse less than A such that B into B inverse is equal to 1 mod A. If A is a prime number and B is less than A, then clearly A and B are relatively prime and have a greatest common divisor of 1. We now show that we can easily compute B inverse using the extended Euclidean algorithm. So we can repeat here, can be solved with the extended Euclidean algorithm like AX plus BY is equal to D is equal to GCD of AB. If GCD of AB is equal to 1, then we have AX plus BY is equal to 1. Using the basic equalities of modular arithmetic, we can say that AX mod A plus BY mod A of mod A is equal to 1 mod A. So if this is 0 plus BY mod A is equal to 1. But if BY mod A is also 1, then Y is equal to B inverse. Thus applying the extended Euclidean algorithm to equation, this yields the value of the multiplicative inverse of B if GCD of AB is equal to 1. So generally the extended Euclidean algorithm can be used to find multiplicative inverse in Zn for any n. So if we apply the extended Euclidean algorithm to the equation, nx plus by is equal to d, and the algorithm yields d is equal to 1, then y is equal to b inverse in Zn. Here we have a table for additive modulo 8, addition modulo 7, multiplication modulo 7, and additive and multiplicative modulo 7. And summary of this says that GF of P consists of P elements. The binary operations plus and multiplication are defined over the set. The operations of addition, subtraction, multiplication and division can be performed without leaving the set. Each element of the set other than 0 has a multiplicative inverse.